Okay, we'll start now. Okay. So then after that, after we had got there, then we realized that that was a that was going to turn out to be a finite error for the n equal to 0 case, and typically, and that we could argue we might have a picture. A picture might look like this. If you say, well, what does that mean in the time domain? Well, what that would mean is that the response, there was a difference between the final value for the input, which for a step function would simply be of course the constant a, the a valued step input, and then the response could very well could and would be expected to eventually flatten out, but with some difference in there corresponding to the steady state error. Okay, so there's some sense that would be a picture that would be consistent with a finite error which was not 0. Now to remind you, there are only going to be 3 cases that will, in a sense, 3 ways that this steady state error will come out. Either you'll get a finite error, as we have here, or which is, you know, so-so in terms of acceptability, or we'll actually get a steady state error of 0, which would be considered ideal or perfect, and the best we could hope for. Or the other case, which we'll see coming a little later, is that we could get a situation where the steady state error blows up, which would almost, in general, would be unacceptable. Okay, so any questions? So that was for the, let me see, that was n equal to 1. That was for the previous page, right? Yeah. That was for the n equal to 0 case that came out. And then and I, stop me if I throw a line across here, but I'm not sure that's where I stopped or where I just put a line there just to distinguish. Then we went to n equal to 1. I thought we did these 2 at the end of last time. So if we didn't, you need to tell me, but I'm believing we went through the fact that if we took n equal to 1 or n equal to 2, and we went back to the original expression for the step input, we saw that in both cases, if you put n equal to 1 or n equal to 2, then even the limit that s goes to 0, 0 plus something is still something, and in the numerator went to 0, so the result was 0. And I think that line of reasoning worked for both n equal to 1 and n equal to 2, so we got 0 and 0 for the n equal to 1 and n equal to 2. And you can say, what would that look like if you had a step input? I would argue it would look like that picture right there. You notice how the y of t actually converges right on top of the a value. So the steady state error is actually 0. Any questions on that? If you can see that picture, I guess you can. Okay, so what comes out of this is a property that seems to thread through even the other cases as we look at them. But let's just summary. We'll summary what we just seen would be right here. We say, okay, well, we saw that for the type 0, we got a finite error, steady state error. And yet for type 1 and type 2, the steady state error was 0. So in words, you could say what this translates into, it would imply, which we'll see that this will be repeated, this idea, is as the type of the system gets higher, the system is better able to track the input. Okay, and that's an idea we'll see repeated here as we go through some of the other type inputs. All right. Any questions so far? Okay, so let's advance to the next input that we could consider. Since we did the m equal to 1, which is a step input, let's do the m equal to 2, which is a ramp. And the first thing we'll do is go back to our Swiss knife of formulas, which covers both arbitrary n and arbitrary m, or n and m. And that was, let me get my pages back in order here. Well, it's on my review sheet. That's all I need, really. Let's see, where's my review sheet? There it is. Okay, so there's my, on the basic equation 12, and it was on my review sheet. So that's the formula we came up with. So what we want to do is we want to set the m equal to, everyone out there follow me? What am I going to set the m equal to? Anybody hearing? What's the m equal to?
2.
Input.
What? Set the, for the, this case, that would correspond to the ramp?
Also 2.
M equal to 2, correct. So if we set the m equal to 2, that's a minus 2 plus 1. I think you can do the arithmetic. That's a minus 1. And then this will be, and that's the only place the m appears. So after setting the m equal to 2, this would be the expression that we would get. The idea being, well, now we've taken the, we made the assumption that the input is a ramp, and then what we can do is look at the effects on the various types. Type 0, n equals 0, n equal to 1, and n equal to 2. Any questions?
So what's the difference between these then? You're just changing the bottom, like instead of making it like a, like the ramp and the step, that's just like changing the m's basically.
Okay, so this may, you know, in some sense, I view it as arbitrary whether you want to do. I mean, in some ways, we're trying to represent the various cases in as organized way as possible. In brief, so one could argue you could start by selecting the type and then change the inputs, or, which I don't see from a certain viewpoint, I don't see what the difference would be in the end. It shouldn't be any difference, but the point is we have to choose one. If we're going to be organized, we have to choose to pick one first, and then the other ones we can change. So in the scheme as it appears in my notes, we're selecting the input type first, or don't use that word, just say the input functional form first, and then we're selecting then we're looking individually at the various system types. Am I answering your question or not? Or I think I realize it could be confusing because, you know, you could argue there's 3 different types for the systems and 3 different inputs.
I was really just asking what was the difference between them.
Excuse me, I didn't understand the last question. Or was
I was asking what the difference between them was, mostly.
Oh, well, okay. Think of it this way. The type is strictly associated with the system, okay? In other words, it's controlled by the system. The thing we call the type, the n, is controlled by what's happening here. The input is, the m is associated with the input. So, I mean, that's about as clear. I mean, I think it's clear that, you know, this is, when you change the m, you're changing the RFS. When you're changing the system type, you're changing the GCG.
Okay.
So there's a big difference right there, if that's the difference you're looking for. Does that help me?
Yeah, that's what I was kind of asking.
Yeah, I mean, I thought so, because, you know, we got these, In a way, you could argue it's arbitrary, you know, that the symbols that are used in the book, but I pretty much prefer to use the same symbols in the book, so that's what I'm doing. So for us, the M is the one that controls the input signal. Okay, so moving the story along a little bit, as presumably we need to, we have the ramp, which is M equal to 2. We argued what happened there. So then all we need to do would be to consider the possible, what happens with the various types. So if we go with type 0, that would be N equal to 0. We don't need to go all the way back to the Swiss knife of formulas because we've already taken M equal to 2, which corresponds to a ramp here. So we'll just use this one. And all then we need to do is focus on where there's an N. And so wherever, since we went for the type 0, that would, if you set N equal to 0, you get S to the minus 1. And then if you set 0 down there, you get S to 0. Any questions? Now that S to the minus 1 has been re-represented, but it's still there. That's it right there. And so we can see that if we look at there's two factors here. The second factor looks like it's going to just come out to be finite. But we can see the 1 over S there. So in the limit that S goes to 0, 1 over 0 is, some people say undefined, but we can say as S got smaller and smaller, it went to the limit of infinity. So here we see the first case where we argued it could happen, that there could be situations where the steady state error is infinite, which means the system isn't tracking at all. You know, the two results are diverging. The input and the output are diverging even in the steady state, when you argue there's no steady state here. Okay, so that's for the type 0. So let's move on to the type 1. And you need to stop me if you got a question. So with type 1, again, we're dealing with the ramp. Again, we're dealing with N equal to 0, N equal to 1. Now it's type 1, so N equal to 1. And so we can go back to our formula that we ginned up with the ramp in mind after we took M equal to 2, but for arbitrary type. And since now in this case, we're selecting N equal to 1, because previously we did N equal to 0, we'll do type 1 system here. And therefore, if we do that, we can see where that S to the 0 comes from, because that's what, N equal to 1, 1 minus 1 is 0. And then and since N equal to 1, that's S to the first part, which is just simply S. Okay, so now again, we see that, okay, we need to take the limit that S goes to 0. And when we do that, basically the first term becomes 0, and then we get this other term, which looks like it would be finite. And then of course, the numerator looks finite because the A wouldn't be, the A is not going to be selected to be 0. It would be a very interesting problem. The ramp essentially would not be non-existent. So the A is there. So basically, this would be the expression that we would get for the steady state. And it looks like one of those cases again where the error is going to be finite, the steady state error. Any question on that?
I do have a question on the A.
Yeah.
So the A, like in a unit step, would be the magnitude of the step. In a ramp, it would be the slope.
Well, I'm not, and hopefully I don't, basically this would be in other words, it's really not a unit step. That's my point. It's a step of amplitude A.
Okay. So it's A times a unit step, basically.
Yes.
Okay. On the ramp, it's just the slope. What is it on the parabolic?
You could argue it's the rate at which it, increases, the second derivative, whatever, so to speak. It controls that. So yeah, the bigger the A, the faster that slope will be, or that second derivative will be. Of course,
Okay.
the slope too.
Got
So it's directly tied. The A is directly tied to the input side, and it's if A were equal to 1, we'd be referring to a unit step. If it was a unit, if we were dealing with a unit step. But the point is that's A could be. I mean, the fact is, like you said, the A for a unit step it would look like this. And then for a ramp, it would be the slope would be increased, et cetera. And then for the parabola, it's like it's the second derivative gets increased. So it increases faster even. So yeah, the A plays a role in all three of them. Did I answer your question or not?
You did. I just did the homework and I was just getting a little confused.
Okay.
There's a lot of assuming A equals 1 in the homework.
Yeah, I'm not sure. Other than the fact that I know that the A in general doesn't have to be 1. It could be, I mean, it's always going to be a constant, but it doesn't have to be 1, a positive constant. Okay, so the recipe for the, it's kind of like the same idea again. You could argue looking at this, well, one way to come up with this constant would be somehow to go back to the GCG and factor that expression that we had with the N of S and the D of S and come up with the so-called the zeros and the poles that appear out of that factorization. However, that's often more work than it turns out we need to do because we can get away with this almost the same kind of trick that we did before. So, but first off, let's note that we can, for the sake of argument, we'll say whatever that is, we'll call it K sub V, where V stands for velocity. If you check the previous case, there was a K sub P, and that P was for position. So what we want to do is we want to find out that there is a counterpart formula for predicting this denominator, which we call KV, and we can get to it in the following way. First off, let's go back and take a look at equation 7. Let's see here, 7 or 1, or not 1, but okay, right. I just need to find that page here. There's 7. Okay, so from equation 7, I don't need anything fancier than that, really. From equation 7, we see there's the form for 7, and we're currently in the discussion where the types that we're focusing on is a type 1. That means n equal to 1. So it would not be incorrect that for that specific type, we can set the n equal to 1, and we can write the GCG product this way, right? If you go back to 7, just set n equal to 1, and you'll see that's what you get. Now from that, you could argue that, okay, if you multiply both sides by S, you get rid of the S in the denominator on the right-hand side, And so you're just left with the ratio of the factored forms here in both the top and the bottom with the products rules, okay, the product. And then you can take the limit. So you do it on the left, you got to do it on the right. You could take the limit that S goes to 0 after you multiply through both sides by S. And you have to agree then, I think, that since this part's the same as this part from the first part of the discussion, all we're doing is now doing the limit on both sides. And we would observe that when we get done with a limit in the in-between one right here, the in-between formula right here, we see that takes us right to that one. Right, because setting S to 0 here, S to 0 there, takes it out of the numerator and the denominator, and we're just left with that quantity involving the product of the ZI and the product of the PK, in the capital K in the numerator. Well, where that is relevant is the fact that that expression right there is identical to the one up here. Can you see that? Anybody see that?
Yeah.
Is that clear? Any
Yep.
questions on that?
Yeah, no question.
No question. Okay. So what we're seeing here is that the same kind of shortcut can be put into place for solving for this ratio here in the case of the ramp and taking n equal to 1. We see, in fact, then because the error is finite, we can get that quantity by, instead of just trying to factor it, we can use this recipe, which is a practical one to use because of how easy it is to use. So our conclusion is that our constant that we need, our so-called velocity constant that needs to go into predicting this finite error would work with that recipe. Now, there's a number of ways to view this in terms of why it's called velocity constant. You can say, well, it's all tied to the fact that we have a ramp. It's like where things are changing with it. It's not like a step where it's constant, like you have a constant position, but now this is where the position is time rate change kind of thing. Or you could almost, I think, equivalently view it from the viewpoint is there's an extra factor of S that goes in the recipe, and we know that multiplication IS corresponds to some sense, corresponds in the time domain to doing a derivative. So, and if one constant is a position, well, you can say the time derivative of a position is like a velocity. So now, however you want to think about it, there is a rationale for the language they're using, calling that a velocity constant. Okay. All right, so let's get to the next page as fast as we can. All right. All right. So on the next page, here's a picture. And the picture is intended to convey the idea of what's happening. Again, we have the ramp input, and then we found out that for n equal to 0, the system, the error blew up, but we found out for n equal to 1, so-called type 1, we've got a finite error. One way to view that is, well, steady state error is that we don't know the details in between. With this scheme, you're not taking the limit that t goes to infinity with the exact solution of the error. What you're doing is you're using the final value theorem. So we don't know the details in between. All we know is that in the steady state, the difference between the between the input, which in this case is a ramp, and the output, which is y of t, is finite. That means they're just, in other words, at some point that difference just stays a constant, but not zero. Any questions on that? So as you might guess, if we had for the ramp input, if for the n equal to 0, we found out the error blew up, the steady state error blew up. For n equal to 1, we found out that the steady state error was finite. Any guesses what might happen for the ramp when we take a type 2 system? Any guesses out there? I'll remind you that the rule is that as the system type gets better, the tracking gets better. If the system type gets higher, the tracking is better.
Goes to 0.
0, correct. That would be a good guess, and we'll see. It's with a little bit of a little more practice, you'll see. Well, that wasn't such a far-fetched guess either. Okay, so yeah, so let's take a look at what's going to happen when we take a type 2, which means in brief we set n equal to 2. Okay, not intended to be too tricky. So we can go all the way back to the Swiss knife of formulas, but that's not necessary. We've already got a good formula for the m equal to 1 case, for the m equal to 2 case for the ramp. So we already worked that out. And that's it. Let's see, that's it right there for m equal to 2. And then we'll take the n also equal to 2 in this case. So we get 2 minus 1 is 1, and then we get an s squared. And as you can see, if you let the s go to 0, you get 0 plus something, which is not 0, which means it's not 0 in the denominator. And you get s to the first in the numerator, which means that the numerator is going to control the limit and force it to 0. So if you wanted a counterpart to this figure that we had for the n equal to 1 case, we could argue that what this would imply for the n equal to 2 case with a ramp input would be, again, we don't know anything about the details in between, but the final value theorem tells us that in fact eventually the input has converged perfectly on top of the input. The output has converged perfectly on top of the input, so the steady state error is 0. Any question on that? Okay, so in summary, this kind of summarizes everything. I'm not sure I need to go through all the details because we just went through them, but there's a good summary of that, and even including our recipe for coming up with a KV, the so-called velocity constant. As we see, as the type went up, the tracking got better, and the best condition was for type 2. Now let's just ask the question, hypothetical question. If if we wanted to say, was there a pattern here when we recognized it? If I had, let's say, a 4th row, one labeled type 3, what might I expect my steady state error to be? Anybody?
0.
What?
0.
What is it?
0.
0, correct. Yeah. Once what you'll see in these patterns, and we'll talk. I'll be a little more specific. There'll be a condition between n and m that'll always give you a finite error. Okay, and if n is less than that condition, then it means your type is not high enough and you end up with an infinite steady state error. And if n is greater than that condition, then you'll end up with 0. I mean, you get great tracking. And of course, type 3 then would be higher than type 2, so we're not surprised. All right. So really, all we've done so far is focus on the results associated with the first 2 columns, even though this table shows all 3. We'll get to the 3rd column in a minute. And I would contend that the entries here are absolutely consistent with what we just talked about. Now we might notice, and this is kind of here's the so-called step, here's the ramp, here's the parabola. We might notice that we get these finite errors appearing on the diagonal of this table. Now, is there one rule that seems to be relating the n and the m, which I just kind of hinted at there is, in such a way that we would always know that when that condition was met, you'd get a finite error. And it's kind of more or less tied to that diagonal. Right? Because if we see that, let's say, for example, and I contend the condition is this one, n is equal to m minus 1. Okay, and I'm just going to throw that out as the condition that if you look at the situation on the diagonal, every one of those diagonal entries will be compliant with that rule. And we can let's check these. So we see that in the first column we would have what? Let's see. Okay, so in the first column I've got m equal to 1. Let's see. So and then I would have n equal to 0. Right. So is 0 equal to m minus 1? If m is 1. What's the answer? Yes or no?
Yes.
Yeah.
Yes, right? Now, if we go to the second column, we see that second column corresponds to the ramp for which m is equal to 2. And I would ask the question, well, then we see, in fact, where that finite error occurred was for n equal to 1. And I would argue, is 1 equal to m minus 1? If
Yes.
m is equal to 2.
Yes.
Yeah. And so you can see it's working. And I contend it'll work on the 3rd one when you try it at home. We're already at home. In your spare time. Anyway, try it on the 3rd one for yourself and convince yourself it's that this particular rule does connect the cases for which you get a finite error. So the idea being that if you know those cases, then it's easy to check the cases for which you get either an infinity or 0. So basically, if n is what? Less n? When am I going to get an infinity? I get an infinity if n is what? Less n or greater than that condition. Remember what's the issue on the tracking? Less than or greater than this condition? You follow me?
Less than.
Less than. So if n is less than m minus 1, we get the infinity. If n, that only leaves, how do I get a 0? And then would be, if you follow me on that, would be then greater than m minus 1, right? You get, then that's the best situation. Any questions on that? No, okay, so my notes, I've got a picture here. This would correspond to, I guess it's conveying the idea if you have like a triangle input sawtooth, who knows. Anyway, the idea is that you have this, this response, which in the beginning, you really don't know, you don't have the details because you're not working out the full transient, but you do know in the steady state for that, under the ramp with n equal to 1, you get a finite error. So eventually it reaches a finite error and stays that way until you get another transition on the input. Okay. Any questions so far? All right. Then I'm going to go and let's just wrap this up with the m equal to 3 case, which would be the parabola. And as we did before, we can go back to our Swiss knife of formulas in this section, which has the general n and m in it, which I think it's this one right here. So we're going to take, for the parabola input, we're going to take the m equal to what? What do we need to take it to, equal to, out there? Anybody out there? Set the m equal to, for parabola?
3.
3. Okay, so set it equal to 3. We see we got a minus m plus 1. If you check the arithmetic, it would be, if m is 3, then that would be a minus 2. So we replace that part in the formula up here at the top with a minus 2. And then we're ready to go with the different types. Now, we can do, before we jump in, we can argue here that, so the m is equal to 3, and the condition would n is equal to m minus 1 is the condition where we get a finite error, right? We just said that a minute ago. So maybe to no surprise, so what if m is 3, what's the value, what's the type that would give finite error? So what type would do that for us here with m equal to 3? What?
It would be 2.
2 would be 2, right? Type 2. Now pretty much most of the focus is on 3 types, 0, 1, or 2. So as we do that, we can say almost immediately, even before we even pull out the arguments based on the expression, we would expect if n is equal to either 0 or n is equal to 1, I would say, based on our current understanding of how this works, ESS is going to be equal to what? You follow me? Since 0 and 1 are less than 2, and 2 is
Infinite.
what? Infinite, correct. So even without pulling out the formulas, we kind of have a advanced idea of what should happen. So I'm gonna, let's see, there's n minus 2. I'm gonna let you check if you put in n equal to 0 and n equal to 1 and take that limit. Yes, you get infinity in both places. So where it gets interesting again, I mean, if you have a question, bring it up. I would say where it gets interesting again is where we have this finite error condition, which we know will happen when we take n equal to 2. Now for n equal to 2, notice what happens. Something interesting happens in the numerator. 2 minus 2 is 0, so that means there's no s factor in the numerator like there was before. And we get an S squared down here, but we'll see that isn't going to make much difference because in the limit that S goes to 0, it goes to 0. So 0 plus something is 0, so you get back the form that we see here. Now, just like before, where we had the constant for position and the constant velocity, this one is called the acceleration constant. And in order to clarify the recipe that sort of allows us to make the prediction of what will happen without doing the factorization on the GCG, numerator and denominator, what we can do is we can go back again to that equation. That was equation 7. And if we go back to that equation 7, again, I have it on my review page here. If we go back to that equation 7, that would, for n equal to 2, that puts a 2 there. Okay, that's the only change that takes place. And we see that the GCG can be represented this way. And we can play the same trick. We can multiply both sides by s squared. Okay, and then you would argue then that the s squared, that part there, is equal to, is going to be, since once you multiply by the s squared, and they still need to take the limit, take the limit s going to 0, that forces the s to go 0 here, and 0 here, you find out that, okay, it looks like if you go through those steps, what comes out of this ends up looking like this, which, surprise, surprise, is exactly in agreement with our presumed acceleration constant K sub A. So this then becomes a recipe for predicting the K sub A needed in the predicting the steady state error. Okay, that's with n equal to 2. And for the parabola. So we got all 3 of them. So if we go back for a moment, we see now that how the steady state errors this summarizes all 3 cases, right? Notice that I'll bring it to your attention. Notice there's a slight difference in the form for the steady state error here in the first one for the step than there is for the ramp and then for the parabola. According to am I about out of time? Or is this, where am I? How much time I got left?
It's already 10 o'clock
It's
now.
10.
Okay, then that's what I was thinking. All right, then we'll stop with this today and then pick up the final, presumably the final part of it on Monday. Okay. Okay. I'm going to be here for, I guess if you have any questions, I'll be here for a few more minutes. Otherwise, I'm going to close the meeting. I'm not hearing anything. Okay, I'm ending the meeting, then see you on Monday. If not, well, there's the 4311 class too. So, yeah, end meeting for all.